away from displacement reaction, we'll look at our next type of reaction called double decomposition. What is a double decomposition reaction? It is a type of reaction where two soluble compounds, especially salts, react by exchanging their radicals and then form two other salts, of which one is soluble and the other is insoluble, volatile, or gaseous. And we have another straight representation of a reaction showing double decomposition. A plus B, AB plus CD, giving us AD plus CB. AB plus CD, giving us AD plus CB. Let us take a look at how that kind of reaction takes place. Examples. We have an example between silver nitrate and sodium chloride. We have sulfuric acid reacting with potassium nitrate. We have lead nitrate reacting with sodium chloride. And we have sodium chloride reacting with sulfuric acid, tetraoxosulfate 6 acid. So let us take a look at the first equation, which will explain every other equation we have here. Silver nitrate reacting with sodium chloride. So when silver nitrate reacts with sodium chloride, silver nitrate come into reaction with sodium chloride. We have sodium chloride. It gives us, this is A, B, C, D. It also gives AD plus CB. So looking at the prototype, this is going to give us silver chloride plus sodium nitrate. We have sodium nitrate, silver chloride plus sodium nitrate. So this is what we have. So we can see their radicals have been changed. So they swapped their radicals, silver and sodium. So silver nitrate reacts with sodium chloride and it gives us silver chloride plus sodium nitrate. Silver chloride is insoluble in water, so it comes out as PPT, precipitate. I like to recall our lesson in acid, base, and salt. So do kindly check back our lesson video on acid, base, and salt. There we talked about precipitation reaction and you will get to understand more. So silver nitrate reacts with sodium chloride to give us silver chloride plus sodium nitrate. AB plus CD gives AD plus CB. So that is the reaction called double decomposition reaction. So all other types of reactions follow the same pattern. They all follow the same pattern. Sulfuric acid plus potassium nitrate, lead nitrate plus sodium chloride, they all follow the same pattern. That is what is called a double decomposition reaction. Having seen that, let us take a look at catalytic reaction. From the word catalytic reaction, it implies that there is the presence of catalyst in the reaction. So catalytic reaction is a type of reaction involving the use of catalysts. Catalysts are substances which are said to alter the rate of any chemical reaction, but itself remains unchanged after the reaction. There are different types of catalytic reactions. They are homogeneous catalytic reaction or catalysis, and we have heterogeneous catalytic reactions. Let us take a look at what we mean by homogeneous catalytic reaction or homogeneous catalysis. When we talk about homogeneous catalysis, it is that type of catalytic reaction in which the reactants, the catalysts, and the products are all in the same state of matter. They are all in the same state of matter, or if we so wish to say, you can say they are all in the same phase. Looking at the first example there, we have sulfur 4 oxide reacting with oxygen. Sulfur 4 oxide is a gas, oxygen is a gas, and the product formed is sulfur 6 oxide, is a gas also. And the catalyst that facilitates that reaction, that is, makes it to go faster, is nitrogen 2 oxide, which is also a gas. So these reactions in which the reactants, products, and the catalysts are in the same phase or in the same state of matter is said to be homogeneous catalytic reactions. The next equation is ester plus water. As you can see, that is ethyl ester reacting with water. Ethyl ester is a liquid solution. Water is liquid. Sulfuric acid is acting as a catalyst and is in the aqueous state. And our product is ethanoic acid in the liquid state and ethanol in the liquid state still. So when reactant products and catalysts are all in the same phase, then it is said to be a homogeneous kind of catalysis. What about the heterogeneous? When we talk about heterogeneous, it is a kind of catalytic reaction in which the product, the reactant, and the catalyst catalyzing such a reaction are not in the same phase. So, for that reason, we tend to have different states of matter. Example is hydrogen as a gas reacts with iodine in its gaseous state, and it gives us hydrogen iodide in its gaseous state. But the catalyst catalyzing that reaction is platinum, and platinum is a solid metal. Vegetable oil can react with hydrogen. That is to say, when we carry out hydrogen, we'll carry out the hydrogenation of vegetable oils. So hydrogenation of vegetable oils gives margarine, which is a solid substance, and that reaction is usually being facilitated by platinum or nickel. That is what we refer to as heterogeneous catalyst. Heterogeneous simply means different, not the same. Hetero, not the same. So, looking at homogeneous and heterogeneous catalysis, let us consider what we mean by characteristics of catalysts. Let us look at the characteristics of catalysts. When we talk about the characteristics of catalysts, catalysts are said to alter rates of a chemical reaction. That is, they can speed it up or they can slow it down. They alter chemical reactions. Catalysts that speed up chemical reactions are positive catalysts, while those that take it down are negative catalysts or inhibitors. So catalysts alter the rate of reactions. Catalysts themselves are not altered during the reaction. They are not affected during any chemical reaction. Catalysts are said not to start up reaction. They don't start up a given reaction, but they only act on a reaction that is in progress. Catalysts are specific in their action. That is to say, they are specialized for a particular type of reaction. Each catalyst knows the kind of reaction it can catalyze. For that reason, when we place a catalyst that is not used to a given reaction, then such a reaction will likely not take place. unless we place in catalyst that is specific for that reaction. We also know that catalysts have no effect on the equilibrium of a reaction. Catalysts cannot influence the type of product that is being formed. That is to say, if a product is to be formed, catalyst cannot detect the kind of product that will be formed. It can only influence the quantity of the product that will be formed in a given time. Take, for example, if A combines with B and the product is going to be T under normal conditions, if catalyst is involved, let's say catalyst is involved, this is our catalyst. If catalyst is involved, catalyst cannot determine the type of product that will be formed. So catalyst cannot say, because I am involved now, T will not be produced. Instead, what I would like to be produced this reaction is W. Catalyst cannot do this. What catalyst can only do is, instead of saying W will be formed, catalyst can only say, I will ensure I produce a huge number. That is what catalyst will say. I will ensure the production of huge number of T under the same 10 seconds. It will take 10 seconds to produce this size of T, but catalyst can say, since I'm involved, in 10 seconds I will produce this size of T. This is what catalyst can do. So catalyst cannot detect the type of product that will be formed, but it can only influence the quantity of product that will be formed in a given time. Now, no matter how small the quantity of a catalyst is, it will still alter any chemical reaction for which it is known for, it is specific for. So, no matter how small, we don't need a whole basin of catalyst to actually alter the reaction that it is specific for, the reaction that it can actually alter. No matter how small the quantity is, it will alter the reaction to some degrees. Now, the strength of a solid catalyst can be increased by increasing its surface area. That is to say, catalysts that are in the solid state, when they are to be used in any reaction, if they are being grounded to powder, the rate at which they will act will be much more faster compared to if they are still in their lump state. If they are still in their clumping lump state. So when catalysts are grinded, it increases surface area for interacting with the reactants and thus bringing about products in a limited time. Lastly, since catalysts don't affect the overall reaction, they are written on top of the arrows before the product. So since catalyst has no influence in detecting the type of product that will be formed from the reactants, catalysts are usually written on top of the arrows for any given reaction. That is, these are the characteristics of catalysts.